I will present to you this paper that we worked in. I am a PhD student, sorry, at Thales Research and Technology and Université Paris-Saclay. And this paper is about the identifiability of a certain class of decision models, hierarchical decision models. So first of all, I will introduce the model and then the main contribution. So the model that we work on is a hierarchical model. This means that we will compute, it's a scoring model, so we'll compute a score for alternatives, and each alternative is defined on criteria. In this example that you see here, you have houses, and they are defined on 7 criteria, which are the dotted circles, so surface area, garden, garage, etc. And rather than computing a single score instantly from all of these criteria, we'll do that by aggregating successively into smaller subsets of criteria. For instance, the satisfaction on the garden and the garage are aggregated into a satisfaction on the commodities, and the satisfaction on the comfort is deduced by aggregating satisfaction on the surface area and commodities. And you can do this successively in order to have kind of a divide and conquer approach and have a much more readable model. And so how do we compute the satisfaction at attribute level, so criterion level? You do this using marginal utilities. So marginal utilities are a small rescaling, one-dimensional rescaling, which will give to any attribute a satisfaction function. We restrict ourselves to very constrained and thus formally constrainable type of marginal utilities. They will be piecewise C1, normalized between 0 and 1, and either monotonic or bitonic. As I said, we aggregate successively, and so we need aggregators at each of the non-leaf nodes, so commodity, comfort, accessibility, and global score. And the aggregator that we use is called the Choquet Integral. It's a model that's been gathering momentum in the machine learning community. And it's basically a weighted sum or a convex sum of the minima of all values. So the minima provide the nonlinearity, which allows more expressivity. And it can be written as such, and thus it is a piecewise convex sum of the values over the attributes. So piecewise convex means that it's linear and its weights are non-negative and sum to 1 everywhere. So basically, you can define a number of regions, R here, and each of these regions will be separated by hyperplanes of the shape one attribute equals the other attribute. This is because, as you can see, it's a weight sum of the mins, and the mins basically switch their weights when the mean changes, and that's when 2 values are equal. So the Choquet integral is continuous, and we generalize this to UHCI, which is a hierarchical Choquet integral for the HCI part, and U for the marginal utilities. So there are marginal rescalings at the leaves of the tree, and then a tree of aggregators of Choquet integrals. So now I present the main result of this paper. So we show the identifiability of the UHCI class of models. So identifiability means the unicity of the parameterization for a given model. That means that if you have 2 models that are equal, that give the same score to all alternatives, then you know there is a single parameterization. Here we have an example in the illustration. You have a class of model C1 with parameters A and B, and the function fab of x returns a times b times x. Of course, if A and B are real numbers and x is any real number, this is not identifiable because you can have 2 equal models with different parameters. If you have 3 and 4, you have fab, f34 is equal to 12x, and f62 is also equal to 12x. So you cannot deduce the parameters from, even if you have all the values on all r for all x. On the other hand, if the model is ax plus b, then you know if you have even 2 values, you can deduce the real parameters. So this class is identifiable. You can see that the identifiability depends on the type of parameterization. You could rewrite C1 with a single parameter or constrain the parameters in order to have identifiability, actually. So in the case of a UHCI, what do we mean by identifiability? This means that if we have f and f primes that are 2 UHCI, all their parameters are equal. So all the marginal utilities at the leaf level are equal. So all the functions will have the same rescaling on any criteria. Well, they will be different from criterion to criterion, but for both models on the same criterion, you will have the same rescaling. Both models have the same hierarchy, so that is the tree structure that I presented earlier. And the fuzzy measures, so the parameters of all of the Choquet integral will be the same. So basically the weight of the convex sum, of the piecewise convex sum, and the borders will be the same for both models. Why is identifiability important, even needed in some cases? Basically, when you learn a model, if you want to have some interpretability or intelligibility in the model, it's nice if you have an answer to your question, but if you have two very different parameterization that have basically no error or that can represent your data set very well, then you can have two conflicting interpretations. And this is problematic because you cannot trust a model if you train the model on a data set. Both are very good and have high performance, but one says that the garden is by far the most important criterion, and the other says that the garage is by far the most important one. So basically, this unicity is very important for trusting the model. In the case of the HCI, so as we saw, the CI is a piecewise convex sum, and so the HCI is also a piecewise convex sum with a slightly more complex borders, because the frontiers, because the affine regions are now hyperplanes, and we have we assuming that the marginal utilities are continuous and piecewise C1, which is not a very strong assumption in decision aiding, for instance, then you have now a UHCI, which is a piecewise C1 function with C1 borders. The idea of our proof for showing unicity is by analyzing these borders, so these C1 functions. Here you have an illustration of how you can obtain the frontiers from a UHCI model. If you are given a UHCI model, given its aggregators, its marginal utility functions, and its hierarchy, you can quite easily deduce the borders. So for instance, you see that node 3 here as a marginal utility in two parts, in two C1 parts, as we saw right here. So F3 and F times 3 in this case, separated by an alpha. It's not restricted to 2 parts only, of course. So you can see that you have a separation border when X3 is alpha, where the function is not C1 anymore. And then you have for A4, which aggregates A1 and A2, you see that if you write it like that, you will have one region where A1 is smaller than A2, in which case you have A1 plus A1 out of 2, and you have A4 equals A1. And you have another region where A4 equals A1 plus A2 plus 2 if A2 is the mean term. So if you look at this, as we said, for a given CI, you change region when two children are equal. So if basically this yield these borders, so A1 equals X2 means this is the border that I just described, and A1 plus A2 plus 2 equals A3 comes from the fact where A4 equals A3 and A4 equals A1 plus A2 out of 2. And you have also a border where X4 equals A1, A4 equals A1, and then you have a border A1 equals A3. So you can deduce the separation frontiers from this writing. And if you now add the marginal utility, if you factor it in, because A3 can have two parts, you have all of these set of separations. You can do it the other way around. So if you are given the separations, you can deduce the model, because basically, as I said, it's a piece. Each aggregator is a piecewise convex sum. So if you take all of the regions of this piecewise C1, sorry, part, not piecewise convex. If you take all of the region of these piecewise C1 and compare it, and you have a separation border every time it's equal to a function that is also in a region of this aggregator. So in this case, it's not an aggregator. And you can see this because then the hyperplanes can be rewritten as a function of x1 with a positive weight, so here 1, and a function of x2 and x3 with a positive weight of half. And then you know that you have on one side a subset of x1 and then a subset of attributes 2 and 3 on the other side. This is basically how you can reconstruct. In this model, it's the other way around. You have a hyperplane that is written as a function of x1 and x2 and on the other side of the equation, a function of x3. So you know that these subsets are separated. In general, you can do this recursively. So you can, at each node, split which are the children from one side and from another. And even if you have more children than 2, it still works. It's just that you will have more separation frontiers, but they will always, you will always be able to separate those subsets given some assumptions, because this is not true for any model, but it is true under very mild assumptions. So the first assumption that we have is H1. So we define by SK the set of subsets of the children of a given node that have a mean term between them. So these are not, it's not a linear model in this case. You need to have a min between these criteria. And so you want all of the children of a given node to be connected by either a min or a chain of min. If you plot the graph of all the terms that interact together with a term as a min, then you will have a connected graph of all the children. This prevents having something that you can, like some kind of uncollapse from a model. Here you have an aggregator with 4 children, with 2 subsets that are not joined by a min, because A1 and A2 are joined, A3 and A4 are joined, but A1, A2, and the set A3, A4 are not joined. So you can basically rewrite this aggregator, this more complex aggregator, but with 3 very small aggregator, and then all the children and all of the nodes respect C1. The second assumption—
Roman?
Yeah.
Less than 1 minute left. You should wrap up.
I can finish now. So basically, the other idea that you need to have at least one min, you need to have more than one term in the aggregator. Otherwise, you have a simple min between elements, and this can be collapsed into the convex sum of mins that we presented above. So in this case, you have this example that can be collapsed into this, and thus the big result of our paper is the theorem that I evoked earlier under H1, H2, and the constraint that I evoked on the marginal utility function. You have identifiability. So 2 equal models will have the same interpretation and parameterization. Thank you very much. And if there are any questions, I'll be happy to answer them.